So last class, before the tablet crapped out on me, we got through amide formation and the up. I talked a lot about it, and I've cleaned up the slides once the tablet cooled down. So those were all posted online. Went through amide formation using acid chlorides or from esters, and that's really what I wanted to talk about with carbonyls. And so what I'm moving on to today is substitution chemistry and elimination chemistry. This is sort of the second last module of the course, if we want to think of it that way. And the reason I'm going to start with substitutions is because Dr. Eichhorn pulled me aside in a hallway this week and said, "Are you going to teach some substitutions this week?" And I said, "Why?" And he said, "It's going to be the next lab." And I went, "Okay, yeah, I'll teach some substitutions." So it's a really good reason. So, what is a substitution? I'm not really sure how to use. When you're defining a word, you're not supposed to use the word. Is switching one moiety, like piece, could be an atom, could be bigger than an atom, for another. It's just like substituting margarine for butter, except with chemistry, which I guess baking is still chemistry. I've taken up watching like the British Bake Off during the pandemic. It's become the thing I do before going to sleep is watching a bunch of Brits argue over how brown their cake is, and it's ridiculously relaxing. It is. It's just ridiculously relaxing. Like it's competitive, but it's not really competitive. So, no, the evil radicals are coming. That's the final module. I end with evil. I'm feeling really old doing this. My father-in-law used to watch this, like even like 3 years ago. No, why would anyone want to watch that? Yeah, maybe I just hit a certain age. I still have fun. Yeah, exactly. Moiety is like a piece, component, domain. Yeah, yeah. And it's a better term than piece, component, or domain. So that's why I'm running with it. So overall, what do I mean by this? What I mean is something like this. If I take this guy, I treat that with acid, and I'm at home, so I can actually use my mouse because I don't have some sort of stupid firewall stopping me from doing things. And let's say that's ethanol, right? Anyone who's not keeping up, same thing. What I get at the end of that there must be like hotkeys for switching the colors on this, but I just don't know what they are. Maybe I need to program that. Is I've swapped an OH for an ether. And notice I kept the color here. So the oxygen and the ethyl group came from the ethanol. And the water came from what was the OH that was on there. I guess one of those H's that's on the water should be blue, but I just wrote H2O. So what we've done is we've swapped things. That's substitution. So there's two ways you can swap things. And this comes down to the idea that carbon can only make 4 bonds. So there's two different mechanisms. The first one we're going to do is we're going to talk about the SN2. This stands for substitution. I have 2 cats with me back here. I will turn on the video and so that, because I know that cats are very popular. There. Let's see if we can see the video there. But I've got two cats in the back of the room here, and they're both just chilling. They actually were unwrapping Amazon packages this morning. Like, I bought my wife a whole bunch of Christmas gifts, and the cats got out there and started ripping open the packages, and then we're dropping off Christmas gifts outside my door when I was trying to work. And we were trying to figure out where all this unwrapping happened. And of course, there were little chew marks on all the boxes and everything. And my computer is up, sitting on a bunch of pens and cables and things. So I'm sorry for what my camera's doing. Okay. So the SN2 substitution is substitution bimolecular. That's what the 2 means. Nucleophilic, because it involves a nucleophile. And it's driven by the nucleophile. But that's what all those letters and numbers mean. No, that's my lunch. You can't have my lunch. Don't get away from my lunch, you little shit. Okay. So, how does that work? Well, remember when I said, I think it was a couple classes ago, neutral molecules tend to stare at each other. Ethanol and our starting alcohol are neutral molecules that tend to stare at each other. That's why we have acid on there. And when in doubt, protonate something. Stick the acid on something. So that's exactly what I'm going to do. I should make that looked a little rounded. I really should not have anything rounded. It's all sharp Germanic angles. Now these rounded Romance Frenchified things. So what we've just done here is I basically made water attached to a carbon. And we've added water to carbocations, but that's reversible. The water can leave the carbocation. And so what can happen here is our nucleophile, which is ethanol, can attack the carbon and kick out the water. You know, it's basically played a game of bumper cars. And it has bumped out the water molecule. And I'm just making it neutral now because I want to make it neutral. So what's really, really key for the SN2 is that this is our rate determining step. I'm going to come back to what that means in a moment. And I'm just going to abbreviate that as RDS. And what that means is that's the slowest step. That's what rate determining means. It determines the rate of everything else. Everything else happens fast. That step is slow. So everything goes at the rate that step goes. It's like my morning starts at the rate I get out of bed. Everything else is pretty fast, but getting out of bed is kind of slow. So in that step, it's a substitution. It involved a nucleophile, and it involved 2 molecules. It involved both the electrophile and the nucleophile. Okay. Now, in contrast to that, nope, I knew it was going to do that. We have the SN1, which unsurprisingly means substitution, mononuclear or monomolecular, nucleophilic. So 2 of the 3 words are the same, but one of the words is different. And so in that same reaction, I'm going to start with the protonated guy. and then ethanol. And then we ended up with the protonated ethanol because ethanol had a H plus, and there's an H plus on the left of the arrow. There needs to be an H plus on the right of the arrow. Well, there needs to be a plus on the right of the arrow. Charges always need to be balanced when you go over these kind of arrows on both sides of it. I'm going to just grab water, use my water to grab the proton. That's what's going to take care of the H plus. And I get my product, which is a neutral ether. Now, this gives us exactly the same product. You get the same product through these two different mechanisms, but these are different mechanisms. Because note that here, this is the rate determining step. That in the rate determining step, only one molecule is involved. The nucleophile is not there. The only thing that's involved there is the electrophile. Okay. That's what I needed to cover for Dr. Eichhorn. Now we're going to look at these a bit more closely. In this case, give the same product. That's exactly it. So I just looked over the chat, and Zach says, like being stuck behind a slower car in traffic. Exactly. If one car in the chain of cars is going slower than all the other cars, then that's the speed everyone goes at. We're going to talk about why, how we know which step is the RDS. We're going to get into that. Right now, you can't. So what I want to do is the first thing I want to do is I want to take apart one of these reactions. Do a slightly different example. We're going to use sodium cyanide, not just for poisoning your friends. It's also a really good way to add one carbon to something. Okay, we're going to come back to why this is SN2. What's the difference between the two mechanisms? You mean, Schaefer? The mechanisms are different, but they result in the same product. So the difference with this one is there's no nucleophile involved. This thing breaks its own bond on its own. And in the previous example, the nucleophile was required to push it out. So here we have active violent displacement of something, and the other one we just had it kind of falling apart. It's kind of like the difference between, the Roman Empire fell to external invasion by Huns, whereas the American Empire seems to be falling to its own internal contradictions. I don't understand. If anyone's understanding what's happening to the United States, I'd really like to know. So what we have is we have an SN2 here because the nucleophile is involved in having this thing leave. So let's just take a look at some terminology, because I'm going to use these terms. I want to make sure we're all on the same page. I'm going to use a different color. I try and be really good about the terminology, because so if any of you are getting lost and I haven't said something, I'm saying a word that you're like, what is that word? What is that technical word? Please stop me, because I have this nightmare memory of a course I took where the professor walked in day one, and it just, I don't know, there was a single word of English there. It was just, jargon. And everyone was just staring at each other going, what the hell is this guy talking about? And so whenever I learned that lesson and I tried to internalize it. And so whenever I try and throw out new words, I try and make sure I've defined them and we can talk about them. So what we have here is we're going to sort of look at 5 different components of these things. We're going to sort of have 5 terms that are important. This molecule is the electrophile. That's the molecule. The whole molecule is the electrophile. This carbon here is the electrophilic carbon. I guess it could be another element, but it's not going to be another element for this course. It is going to be carbon. We've actually seen sort of electrophilic oxygen when we did ozonolysis and things, when nucleophile attacked that. But it's the atom that is being attacked. This guy here, we're going to call the leaving group. It is called the leaving group because it is leaving. That makes sense. Sorry, there should be a plus I minus. Now, no, I haven't used enough purple in this lecture. This here is the nucleophilic atom. In this case, it's a carbon. It could have been anything else. It's where the electrons are. Where are the electrons coming from to do the nucleophilic attack? Which atom are they on? That is your nucleophilic atom. This whole molecule together is your nucleophile. So what we have here is we have a nucleophile and a electrophile reacting together because the nucleophilic atom is attacking the electrophilic carbon, kicking out the leaving group. Okay. So those of you who are, eagle-eyed, addicted to organic chemistry, and I know there's at least 2 of you in this group right now. Notice that in the first example I opened to start the class, we didn't have any stereochemistry. In here, I do have stereochemistry. And if you notice, we had an iodine, which was an up wedge, and now we have a cyanide, which is a down wedge. And I didn't make an accident there. That wasn't a mistake on my part. That is exactly how this happens. Yeah. Victoria is giving like a really good running commentary on the lecture. So what's happening here? Well, let's think about what this looks like. So I'm going to simplify this example. No, you know what? I'm not going to simplify this example. We're going to stick with this example. It's a good example. So we have carbon. Oh, no, I'm going to learn my lesson. I'm going to start a new page. We've got carbon. It's making a sigma bond with iodine. It had a methyl group. I'm not going to worry too much about I'm not going to worry too much about the stereochemistry. I might be drawing the enantiomer. If so, I'm sorry, but it doesn't really matter. So we have that. This we can think of as our sigma orbital. It's got electrons in it. This molecule has a sigma star, and I know you guys were talking about this earlier. So this is your LUMO. This is your HOMO. And the reason why you have a LUMO and a HOMO here is because this carbon-iodine bond is your weakest bond. Since it's in this molecule, since it's the weakest bond in a molecule, that means its electrons are in the highest energy state. Strong bonds, stable electrons, low energy orbitals. Weak bonds, unstable. The electrons are in a higher energy state. And as we started, I think, lecture 1 of this class, when you make a bond, you make an antibonding orbital, and a bonding orbital equal in distance from the original 2 orbitals. So the weakest bond has the most accessible antibonding orbital, which makes sense when we think that an antibonding orbital is where you put electrons to break a bond. And if you're going to break a bond in a molecule, it makes sense to break the weakest bond. So it's nice that everything kind of ties together so that the weakest bond has the lowest lying antibonding orbital, and that's what we see here. And what does that look like? Well, it's a sigma star orbital. So it's an antibonding sp3 interaction. So that's shaded. No, I don't want next. I want that to be shaded. Yes. Thank you, Alexis. Or chapter 11. Or maybe 15. It's a good question. I got my textbook right next to me. It's in the syllabus, which is my standard answer for everything. Even better when I'm right. Chapter 11. Close. You saw the term nucleophile and jumped to that one. I think there are nucleophiles in there, but that's using double bonds as nucleophiles, and I think we've already done 15. So, again, everything else is the same. We're just doing that bond. Okay. So, if you're a nucleophile wandering around, your cyanide, you've got a triple bond to the nitrogen because you're cyanide, and you've got this big juicy lone pair sticking out the other end. And cyanide's a really good nucleophile because, well, for lack of a better term, it's shaped like a stick. I get really technical here. And it's shaped like a stick in that there's not a lot of bulk. Like all the electrons, all the A value, man, I'm drawing that weird. Like even I can't follow that three-dimensional logic. If you want to draw out cyanide, looks something like that. And you got this nice, big, juicy lone pair. It's negative. It's out on a prowl. It is looking for an accessible antibonding orbital. And of course, when I've drawn the bonding orbital, I'm a little bit lying about this. So I'm going to correct this a little bit. What I'm going to do is I'm going to make the iodine lobe bigger and the carbon lobe smaller. And the reason I'm going to do that is because most of the electrons are on iodine. In a carbon-iodine bond, is polarized towards iodine, which means that in the antibonding orbital, the iodine lobe is going to be quite a bit smaller, and the carbon lobe is going to be quite a little bit bigger. And so you got this lone pair, you've got this low-lying sigma star, and this wants to come and make a sigma bond. And so what's going to happen is the carbon is going to start making a sigma bond with the iodine, with the incoming cyanide. But it still sort of has a sigma bond with the iodine. But it can't do that because it still has sigma bonds with the methyl and an ethyl and a hydrogen. And you can't make, and if you're counting at home, that's 5, and you are at home, I don't know where you are, that makes 5 bonds. And carbon can't make 5 bonds. So this is not a valid Lewis structure I'm doing. But that's okay, because what we're doing kind of is we're interacting with an antibonding orbital. And yeah, when you include that antibonding orbital, that's a 5th orbital. But you're not going to be including that antibonding orbital for long because it's very, very unstable. Because if you have electrons in there, things want to break apart. Everything wants to fall apart. And so one way we can think about this is what's called a transition state. This is not an intermediate. This is not a valid Lewis structure. You cannot draw a valid Lewis structure with those bonds because you'll be drawing 5 bonds to carbon, and that's not cool. There's an overall net negative charge on here. That negative charge is dispersed between the iodine and the carbon of the cyanide. They're both slightly negative. The cyanide was negative, now it's making a bond. The iodine was neutral, but now it's becoming negative as it starts breaking a bond and taking the electrons with it in that carbon-iodine bond. And we can argue that this central carbon here is very slightly positive. I'm just going to make it a full bracket. Another way to draw this. Now, take a look at what these poor atoms in the middle are doing. They were kind of coned out to the left. Now they're flat, right? You have this new bond that's forming between the cyanide. You have this new bond that's forming between the iodine. There are electrons everywhere. And all the methyl, ethyl, and hydrogen want to do is stay as far away as possible from all the other lone pairs of electrons. That's why we do all that geometry, right? That's why we do a tetrahedron. And the way they can do that right now when there are electrons on both sides is for them to go flat. So they're all directly in the plane of my arm, I guess, for lack of a better term. And you have something that really looks like it should belong with a metal in the middle instead of a carbon atom. But you've got a carbon atom. I'm going to make that slightly positive. That's really shitty delta. What time is it? Okay. That cross of Lorraine means a transition state. I don't know why the cross of Lorraine has become to me a transition state. I have a feeling it's because someone who was working with a typewriter thought that it looked a little bit like a T, and it was the one thing they could find on a typewriter that looked a little bit like a T but wasn't a T. But that's just my guess. I have absolutely no idea why that's the case. So this is the transition state, but it's not going to stay like this. We're going to make the cyanide bond and break the iodine bond. And so this resolves into cyanide being on that side. And now our atoms have coned out the other way. So what I mean by that is they kind of formed a cup pointing one way with the iodine sticking out that way. And now they formed a cup facing the other way with the cyanide sticking out the other way. And it's because they passed through that middle phase. And so this is why we have the cyanide coming from the opposite side of the iodine, because the cyanide's interacting with that antibonding carbon-iodine orbital. And that antibonding carbon-iodine orbital is on the back side of the carbon. And so this gets called backside attack, and then people giggle, and then we move on. And so we keep giggling. But what we have here is an inversion of configuration. Sometimes I sort of despair. I find it kind of funny at how obscene and wrong some of the analogies often used in chemistry and descriptions used in chemistry are. But, for the longest time, I was buying my TLC plates from a company because they were the cheapest ones available and they were good. I now buy them from China because they're even cheaper and they're still really good. And the company was called Analytical Technologies, but they decided to abbreviate themselves as Analtech, and their logo looked a little bit like a rectum. And they've been in existence since the 1940s with this logo and this name. And of course, they must have known exactly what they were doing. Like, there was no way they couldn't have known what they were doing. They were bought about 5 years ago and they changed their name, which is really unfortunate. So, they've changed the logo and the branding on all the equipment, because it was always really good for a laugh whenever it was somebody's first time seeing this. And just that company decided to go that way. But it was memorable. And I guess that's what you need to do when you're selling things. So anyways, SN2 proceeds by inversion of configuration. And it's because you have this attack of the antibonding orbital. So what does this look like? So what we're going to do is our first reaction coordinate diagram. So you can draw these for any reaction, but we've kind of not yet. So it's a two-dimensional. If you're a better drawer than me, it should be two-dimensional. Like mine's off at some sort of weird-ass angle. It should be 90 degrees. I'm sure there's a way for me to tell the pen to draw a 90-degree angle. The y-axis is energy. The x-axis is this vague thing called a reaction coordinate, which is kind of like time, but not, because it's not to scale. What we have, and so the reaction we're going to do is we're going to do the one we just did, except upside down because I started drawing the wrong way. Goes through a transition state. I have made my life difficult. Okay, my three-dimensional drawing is awful here. Overall negative charge. The overall negative charge is important. If you miss that, you're wrong because there's a negative charge. You don't need to write in the deltas. Unless I'm asking you to write in the deltas. Goes to product. So this is our starting material. I guess you could call it reactant, but I always call it a starting material, or SM, because we love abbreviations. Yeah, there are all sorts of groups of cyanide I cannot remove. We're going to be talking about relative strengths of different things. Cyanide was negatively charged, and now it's dumped electrons into this. So the cyanide brought a negative charge with it into the transition state, and so there's an overall negative charge in there. That negative charge is distributed on both the iodine and the cyanide. Because the cyanide is losing its negative charges, it's making the carbon cyanide bond, and the iodine is pulling the electrons that were in the carbon iodine bond. Those are going on to iodine. So iodine is going to pick up the two electrons in the carbon iodine bond, making it I minus. And the cyanide is becoming neutral by donating its extra electrons to the carbon. So we have a starting material. As the reaction proceeds to the transition state, it follows a smooth curve. And if you're a better drawer, it would be smooth. It shouldn't be like doing wiggle, wiggle, wiggle. Okay. Up to the transition state. Then down to the product. And so what we have here, why is cyanide point doing dashed line? I can't parse that question. So we want to retype that back out, Nulia. I'll try and understand what you're saying. So what we have here, why is it down here? Because it's coming from the back side of the carbon iodine bond. If the carbon iodine was up, the cyanide has to come from the opposite side. That's what we were just talking about. That's why it's down. So we have a starting material. We put energy into the system because we are paying costs. What we're doing is we're breaking a bond. Breaking a bond takes energy. So you're putting energy in to break the bond. The cyanide is coming in, it's forming a bond, but now you've got an awful lot of electrons all really close to each other, and the electrons are all repelling each other, and that takes energy. And you haven't fully formed the bond, so you don't get all the energy from the bond formation yet. So your bond energy is climbing until you hit the transition state. This is a local maxima. So if you remember all your, not a local maxima. And so if you remember all your calculus, I don't, but hopefully you guys do, then your local maximum is basic are transition states. Your local minima on these kind of reaction coordinate diagrams are intermediates, starting materials, and products. So you get the maximum. This is we think about we're drawing them. We draw transition states, and we always think about we're drawing stable things. The transition state is the least stable thing you can draw. It wants to go either direction. It either wants to make the carbon-iodine bond back again, or it wants to make the carbon-carbon bond. What it doesn't want to be doing is splitting its time like this and not making either one of those bonds. So this is an inherently unstable thing. It doesn't really exist. It's something things pass through. And nothing rests at the transition state. It reaches it and immediately decays, rolling down the hill to either side. And one thing it can do is it can roll down the hill back towards the starting materials, and the reaction goes back. Like the cyanide starts coming in, starts making a bond, and then falls off because you're needing more energy to make the bond stronger. Because as the cyanide gets closer and closer to the carbon, the iodine starts pulling away, and you're putting more and more energy in until you hit the transition state. And if cyanide gets a little bit closer, she's got enough speed or something, and it actually is speed, then it can bump over the transition state, and then it starts falling down the route towards the product, rolling down that giant hill. Looks like a great tobogganing hill. And you're breaking the carbon-iodine bond. The iodine is now falling apart. The cyanide bond is strengthening, and every little distance that the cyanide is getting closer, the iodine is getting further away, and you're making the stronger bond. And then what we have overall is the product is lower in energy than the starting material. And this is your delta G of reaction. This is the Gibbs free energy of reaction. That's what it means, is the difference in energy between your starting material and product. This is the delta G of activation. The activation, energy of activation. You could also call it the delta G to the transition state. Don't really care. Yeah, no, this is exothermic. Sorry, is there ever a case in the product force? Yes, I didn't follow the argument. Bennett, yes, there is cases where the product has more energy than the starting material. Noah is correct that that's endothermic. And yes, we are going to do things like that here. Sweet. Because what we're looking at here is the energies of these particular molecules. But what you can do is you can couple this with other processes. So you can couple an endothermic process with an exothermic process and get an overall favorable process, even though one of the steps is endothermic. This one's exothermic, though. So very straightforward substitutions that we're going to be covering in the immediate future are all generally going to be exothermic. Because otherwise, the reaction would go backwards. Where the iodide that you've just released would come in and displace the cyanide. And that's not going to happen. And the reason it doesn't happen is because that's endothermic. Yeah, EA is activation energy. Sorry. Activation energy. So, this is still something that I try and talk to my graduate students and postdocs about, and we get into long arguments about. But it's really simple. It's not really simple. That's a lie. This is kinetics. This determines kinetics, how fast something happens. This determines thermodynamics. Where it ends up in the end, basically. Do we get the same product if there was no stereocenters? I'm not quite sure how to answer that question. You wouldn't notice an inversion of configuration. There would still be an inversion of configuration. It just wouldn't matter. So if that was a methyl group and a methyl group instead of an ethyl group and a methyl group, you would still have inversion of configuration using the SN2. It just wouldn't matter because the molecule would be achiral at that point. I actually think this is a really, 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 really important slide. I got confused over what was the difference between kinetics and thermodynamics for years, well into my PhD. But it really comes down to this. The delta G of activation, the distance between a starting material and a transition state, determines how fast something's going to happen. The distance between a starting material and a product determines what's going to happen in the end if you let this thing go for an infinite amount of time. The world is always going to end up in the most stable form. But the most stable thing is not always the fastest thing to happen. Okay. And we're going to be talking about these differences and how those two ideas play in together. So this is the SN2 reaction that we've done. Now we're going to do an SN1 reaction. I'm going to use the same starting material. I'm going to use a weaker nucleophile, and we'll talk about why. So my favorite weak nucleophile is ethanol. And I'm going to need to add heat because this is not a very reactive reaction. It does not really want to go. What's going to happen is this is an SN1 reaction. So the leaving group is going to leave on its own. It's not going to be pushed. It's going to jump. We're going to get a carbocation. So what do we know about carbocations? We know they're flat, right? I didn't draw the hydrogen in, but there's the hydrogen. And it's not that I'm not drawing stereochemistry because I'm bored. I'm not drawing stereochemistry because there isn't any. The p orbital is directly into the plane of the page. It is the one lobe is sticking out of the tablet into my face. The other lobe is sticking below the tablet towards my feet. This is a flat molecule. This is not a transition state. This is an intermediate. It is a valid Lewis dot structure, which lets me know it's an intermediate, not a transition state. And now ethanol is going to come in. It can come in from the top face. It can come in from the bottom face. It doesn't have this selectivity. Like in the previous case, the cyanide had to come in from the antibonding orbital of the carbon-iodine bond. We don't have that. We got two equal lobes on these p orbitals. So ethanol can be pointing up. Ethanol can be pointing down. It is a racemate, which means you have a 50-50 mixture of both enantiomers present because there is no preference to make one or the other. No, it doesn't have stereoselectivity. It does have regioselectivity. Regioselectivity is which carbon gets attacked. Stereoselectivity is which stereoisomer you make. We're attacking the same carbon, so it is regioselective. It's just not stereoselective because we get a 50-50 mixture of the two. So it has no stereoselectivity. I'll make a note of that. No, that's a really. I'm really actually glad you said that because it's been a little while since we've talked about these terms, and I don't get too hung up. Well, they're important terms. We all have different things we like, and I know that Dr. Eichhorn really likes stereoselective and stereospecific and regioselective and regiospecific and chemoselective and chemospecific. and we're not really talking about the last one. I have other fetishes. I really like resonance. That's my thing. So we're not done here because this thing's still charged. So I'm just, I'm going to rewrite racemate somewhere else. I don't know, over here. And, a little bit of water or a little bit of I minus, or, more likely another equivalent. There's no water here, so there's ethanol. Just going to use another molecule of ethanol to take away this proton. It's going to do it for the other enantiomer too. So we're going to get a 50-50 mixture. This will probably be one of the only times I draw both enantiomers because they just can't be bothered most of the time. Thank you, Mohammed, and thank you, Bennett. You're both absolutely right and good ways of thinking about it. That carbocation is flat. The ethanol is 50% from the top, 50% from the bottom. There is no preference. Okay, so we're going to finish by drawing a reaction coordinate diagram for this thing. And this is SN1. So that's going to go up into the top corner here. Energy up. You got to put the energy up thing because you got to label your axes. Reaction coordinate. You can shorten reaction as RxN, which I know the pharmacists use for like prescription, but that's silly. RxN definitely means reaction. We had it first. So we have a starting material. There's a hidden transition state in here. I didn't draw the transition state. You know what? Some of them are chemists. The good ones are chemists. I'm going to draw a starting material slightly higher in energy. So I got somewhere to go. You can be a pharmacist and a chemist, or you can be a pharmacist and not a chemist. There was a transition state here, and we didn't draw the transition state. So what is the transition state? I'm trying to draw them kind of over where the thing they're supposed to be. Well, the transition state is when I've started breaking the iodine bond, but I haven't broken it completely. And so, okay, here's a valid argument that we want to talk about. I haven't broken it completely, so there's still some energy in that bond. So isn't that a good thing to have energy in that bond? Isn't that stabilizing? Why is that higher in energy than not having to bond at all? Well, it's because there's not a lot of energy in that bond. You've had to put a lot of energy in to break it, but that iodine is still nearby the rest of the molecule. And so the electron cloud around the iodine is still bumping into the electron cloud around the rest of the molecule. And so you've got electron cloud repulsion. So the transition state for a leaving group leaving is when you've almost completely broken the bond, but the electron clouds are still kind of close together. And now, as you pull further away, the energy benefit of moving further away from the electron cloud is better than the energy loss that you're finally breaking the bond, putting the last little bit of energy in. Like, by definition, this is the worst place you can be. This is the most unstable place. Either it's going to snap back, ouch, this pen is very hard. Either it's going to snap back, right back to the carbon, or it's going to drift off to infinity. We're right here at the teetering point. How is this flat? It's got an empty p orbital. It's got a p orbital. Just that carbon is flat. So it's got and my p orbital is right where my arrow is. I'm really glad you're asking these questions, Nulia, because you're not the only one thinking these, and I really, really appreciate you asking these for the class. Thank you very much. So that p orbital is directly, it's got two giant lobes, and so that carbon is sp2. All carbocations are sp2, and all sp2 atoms are flat. So it's kind of got like three sp2 bonds, each 120 degrees away from each other in the same plane, and it's got an empty orbital. So that carbon is absolutely flat. So we have this intermediate. Then we have another transition state as we go. It's in the middle of that arrow. Again, we didn't draw it. And then we come down to another intermediate. What does this transition state look like? Well, it's going to have the ethanol coming in. Now we're at that dangerous point where the electron clouds are starting to bang into one another. But we haven't put a lot of energy into making a new bond yet. So we've had to put energy in, bring the ethanol in closer, closer, closer. Bond wasn't really being formed, bond wasn't being formed, bond wasn't being formed, but the clouds are getting closer, so we're starting to put more energy in. Now we're at the point where the bond's just starting to be formed. The electron clouds are still repulsing each other. If we move any closer, the bond got stronger, and that became more important than the electron clouds repulsing each other. Now we're going to get sucked in, and we're going to fall down the hill towards this intermediate because we're going to make the bond. Because we've kind of reached that point of decision where either the ethanol is at a 50-50 shot. And that's what a transition state means. Basically, it's a 50-50 chance of it drifting away or it coming in. At that point, it's trying to make that decision on what to do. It comes in, we make the intermediate. Now we have another transition state. And that arrow is a little bit further away, so this transition state is quite a long reaction coordinate away. And we fall down to the product. And this transition state here is of a molecule of ethanol coming in, removing that extra proton. And again, there's a little bit of positive. Everyone's got some positive charge here. That hydrogen's kind of split. We put the energy in to break that hydrogen ethanol bond, but we haven't yet made the new hydrogen ethanol bond. But the electron clouds are getting close together, so we brought things in closer together and they're repelling each other and everyone's unhappy. And again, we're at a 50-50 shot. Transition states are always a 50-50 shot of what just happened. Resume slideshow. Good. Transition states are always a 50-50 shot of going forward or backward. Always, 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 always. If you go backward, you go back to this intermediate. And the most likely thing this intermediate is going to do is go back up to this transition state, because this transition state is lower energy than that transition state. So everything is lazy. Think of water filling spaces. Molecules are the laziest things you've ever seen. They want to take the easiest route from point A to point B. Whereas if it falls to the right on a 50-50 shot, it falls down to the product. And this is much lower energy than anything we've seen so far. And so although a small, and this is why I say everything's in equilibrium, molecules can move back and forwards along this energy surface. They can go to the left, they can go to the right. But give stuff long enough, and it will all end up down here, because this is the lowest energy point. And everything wants to be lazy. And they want to just crash on their couch and lie there. And that's why chemistry is downhill and goes towards products. No, all the transition states are actually different in energy. All three of these are different in energy. If they look the same, it's because I made a mistake. So this one is slightly lower than that one. And so, yeah, the first one's highest. And so when we're trying to determine the rate determining step, what makes a rate determining step? It's the one with the biggest activation energy. And what is the activation energy? It's the distance between the previous starting material or intermediate and a transition state. So this is a delta G of activation. This is a delta G of activation. We can call it E. You know what? I can write delta EA, delta G, delta G EA2. We can call it EA1. We've got a delta G EA3 over here. And like we have sort of a delta G EA minus 1 if you want to go the other way. You can draw activation energies going backwards. There's a net positive charge here. The auction is donating some of its. I got the question from Anita. Can you please repeat why the auctions of the ethanols are slightly positive in a transition state? So that's this one here. So this oxygen has 2 electrons in this carbon oxygen carbon bond, 2 electrons in this oxygen carbon bond to the ethyl group. That's what it all wants its electrons to do, right? It wants all of its other electrons to be lone pairs. But one of them is not a lone pair. It's sharing electrons with the hydrogen. So the oxygen doesn't have full control over its 2 electrons. It's only got 1.8 because 0.2 is making a bond, and so it's positively charged because it's a little bit short of electrons. And the H plus does not have a full 2 electrons making a bond to it. It's only got a little bit of electrons from the left oxygen, a little few electrons from the right hand oxygen, so it's slightly positive. And the left hand oxygen over here has the same problem as its buddy over here. So nobody is happy in this situation. There's kind of a positive charge spread over, like smeared over this entire space. Yes, the first is the highest. And if I drew better, that would be clearer. And we can think of it that way because we're thinking like, okay, how do I know the first is the highest? So here's the question I've got. When we talk about charged species, when we were comparing acids and bases and what stabilized charges, we looked at the charged species and went, how happy is that charge? And that's exactly what we're going to do here too. I want you to look at all the intermediates and think, which of these intermediates, or even starting materials and products, everything, which is the least happy? And hopefully you're thinking neutral, neutral, great. Neutral's fine. Neutral's happy. Don't care. This guy, the oxygens in this guy, in this intermediate here, have their full octet. The positive charge is on an atom with its full octet. That's okay. The positive charge of this carbocation is on an atom that does not have its full octet. So if I have a choice to be an atom with my full octet, like an oxygen, or a 6 electron positive charge like this carbon, I really want to be the oxygen. That looks happier. It's a more stable positive charge. So this is the least stable. And since it's the least stable, it's the highest energy. And a transition state leading to the highest energy intermediate is the highest energy transition state because it has to be higher than that intermediate. So when you're trying to figure out what the rate determining step is, you're looking for where is the least stable intermediate in this entire pathway. And the step leading to that is generally going to be your rate determining step. And I say generally because it does depend on the delta. So if this, for whatever reason, was really high energy, then it might not be a rate determining step. But it's not. It's a relatively stable molecule, so it is. Okay, we're at about we're over actually, we're 2:30, but I didn't want to interrupt this flow. So I think we're done for the day. Have a really good weekend, and I will see you next week.